Hello everyone, welcome to the course of Instrumentation and I am Ishu Gupta. Here we are going to study thoroughly each and every technique that are used in analytical chemistry. So I am here to start with the most versatile technique, that is atomic emission spectrometry. So whenever an analyst is faced with the question which elements are present and at what levels in the sample, so the most probable technique that came into the analyst mind are based upon atomic spectrometry. As the name implies, atomic spectrometric technique involve detecting, measuring and analyzing EMR, that is either absorbed or emitted from the atoms or ions of the elements of the interest in the sample. So the quantitative information means कितने लेवल पे कोई भी आयन और एटम present at what level is derived from the amount of electromagnetic radiation that is either absorbed or emitted by the atom or ion of the interest, whereas the quantitative information which type of element is present in the sample is obtained from the wavelength at which the electromagnetic radiation is absorbed or emitted by the atoms or ion of the interest. So what is the basic principle? As we know, the detection and measurement of emission of electromagnetic radiation can be more easily described once the nature of atomic and ionic spectra is fully understood. So here is a simplified Bohr model is given. As we know कि atom consists electrons, protons and neutrons, in which proton and neutrons are in the nucleus of the atom and electrons evolving around the nucleus in discrete orbitals. So whenever energy is given by outside sources, the lowest energy electron, it is also called the ground state. Ground state electrons get excited and move into the higher energy level state when it in which it becomes unstable and it's when it becomes unstable, it's go back to its lower energy state by emission of the electromagnetic radiation. So here is one more thing. When an ion or when an atom gets more energy, it got ionized. The electron is permanently go out from the lowest energy orbitals and the atom get ionized. This process is called ionization and the resulting particle is called an ion. For example, so here is a simplified view of excitation, ionization and emission process. The horizontal line, this one is the ground state. The horizontal line in this diagram represent the different energy levels of the atom. The vertical rows represent energy transitions. The energy difference between the upper and lower energy levels of the radiation transition determine the wavelength of the radiation. Okay, so here is the ground state, here is the excitation state. When it get more energy, it get ionized. तो आयन की ग्राउंड स्टेट यहाँ पर है, आयन की एक्साइटेड स्टेट यहाँ पर है. वैन यहाँ से यहाँ आएगा तो आयनिक इमिशन होगा. यहाँ से स्टार्ट किया, यहाँ से यहाँ आ रहा है, then it will release EMR of lower radiation. That is also called atomic emission. So mathematically, the wavelength of the emitted radiation is given by the following equation, that is lambda is equals to hc by difference between the higher and the lower energy levels of the electron. So here h is the Planck constant, which has the value 6.626196 into 10 to the power minus 27 per second. C is the velocity of light. The value is 2.99793 into 10 to the power 10 centimeter per second. And E2 and E1 is correspond to the energy in Earth in the upper and lower energy states of the electron respectively. So in atomic emission spectroscopy, UV visible region of EMR spectra is used for the detection. So the value of EMR lies under 160 to 800 nanometers. So here is the source. So here is the atomic spectroscopic sources for atomic emission spectroscopy. So the flames and furnace and electric discharge are generally considered as the three thermal sources used in analytical atomic spectrometry to transform sample molecules to free atoms. So let's start with the flames and furnaces. Flames and furnaces are mostly hot enough to thermally dissociate most of the sample molecules into free atoms, with the exception of refractory compounds such as certain carbides or oxides. Breakdown of these molecules require temperature that far exceed the upper flame and the furnace temperature of typically 3000 to 4000 Kelvin. Because of the temperature limitation of the flames and furnace, the free atoms produced in them are in the ground states. They are mostly suitable only for AAS, that is atomic absorption spectrometry. Here are alkali earth matter elements are mostly the only two exceptions, as their lowest excited states are low enough that even the energy provided by the flame and furnace can excite. So like talk about the third one, electrical discharges, in which PCRs and AC sparks are used formally. So these electrical discharges are formed by applying high electrical currents or potentials across electrodes in the inert gas atmosphere. The temperatures achievable this way are generally higher than those the traditional flame and furnace system. So and after that the IBC source came into force, in which a plasma state is used. So what is a plasma state? A plasma is any form of matter, mostly that is gases, is appreciably ionized. That is to say, a matter consists containing fraction greater than 1% of electrons and positively charged ions together with neutral species, radicals and molecules. Electrical plasma is used only for analytical OES, that is optical emission spectrometry, and highly energetic ionized gases. They are normally created with inert gases such as argon and helium. These plasma discharges are considerably hotter than traditional fan furnace that are used not only to break down almost any type of sample molecule but also excite or ionize the free atoms for atomic and ionic emissions. Currently, the state of art plasma is the argon-supported ICP, that is inductively coupled plasma. The plasma also includes that direct coupled plasma and microwave-induced plasma. So in further lectures, we will discuss these in details. So till then, thank you so much and keep learning.